Hello, good afternoon, everyone. Thank you for being on time. Let's get right into it. Today, we're going to be starting lecture number two, which is on macromolecules. Before we begin with the biology aspect of macromolecules, I have to go through some basic chemistry concepts with you. Some of these things you might have already done in your chemistry class, and it will be a good review for you. And there will be some that might be a little bit new as well. So let's get started. First of all, matter. What is matter? Matter is anything that takes up space and has mass. So it's going to have some volume associated with it, and it's going to um, weight a little bit. Okay? And together, that basically what makes up matter. Now, matter can exist in different states. It could be a solid, it could be a liquid, or it can be gas. And of course, they could cycle between these states by absorbing heat or releasing heat. For example, if ice cube absorb heat, then it's going to become liquid water. And then if you heat it again, it's going to become water vapor. Right? So they're not restricted to a particular um, state necessarily. All matter is composed of elements, right? And elements are substances that cannot be broken down into other substances. We'll take a look at what that means in a bit. Now, atoms, if you remember the hierarchy of organization that we talked about in lecture one, atoms are the basic building blocks of everything that exists. Okay? They are the smallest unit of an element, and it will have the same property, same chemical and physical property as the element. So let's say we look at the element carbon. Okay? So carbon is made up of carbon atoms. Okay, and the carbon atoms will have the same chemical and physical properties as each other, and the entire carbon sample will also have that same property. Right? And so the smallest unit of the element is the atom. Now, what makes up an atom, though? If you look into the internal structure of an atom, there are three basic things that makes it up. There are protons and neutrons. These are going to be together in the center of the atom. Right? It makes up what we call the nucleus. Protons are positively charged. P for positive and P for protons. Neutrons are neutral. They have no charge. And circling around the nucleus are negatively charged electrons. Right? So these are negatively charged. And they're kind of traveling in their own orbits. So every atom will have protons, neutrons, and electrons. The number of these things is going to vary from one element to another element. If you look at the number of protons in carbon, that's going to be different than the number of protons in, say, nitrogen. Right? But they're all made up of these three things, just at different proportions. So how do you know if something is an element or not? Well, that's where the periodic table comes in. If you can find it on the periodic table, then it is going to be an element. Right? So you might recognize some of these symbols. If you don't know yet, you will probably know all of them. Um, well, not all of them, but like you will be more familiar with most of these after you finish your chemistry course. So C here is carbon, right? That's an element. Oxygen is an element. If you can find it on this table, then it is an element. Something like water, which some of you told me is H2O, that's not an element. We cannot find H2O anywhere on the periodic table. We can find H, we can find hydrogen, we can find O, but we do not find H2O together. Okay, so the periodic table shows all the elements that we have discovered so far, and as far as we know, up to this point, everything in the universe is made up of these elements. Okay, so you can see there are hundreds of them, hundreds of elements. But for the human bodies, it only takes five of these elements to make up over 96% of our body. Okay? So even though there are hundreds of these elements that exist in nature, over 96% of our body are made up of just five elements. So they are carbon, nitrogen, oxygen, hydrogen, and phosphorus. Okay, so carbon is like charcoal is made of carbon. Right? If you have a pencil, the tip of the pencil, that stuff, that's graphite, and it's made up of carbon. Um, Carbon can come in very expensive form too. Right? Um, does anybody know a very precious gem that's made up of carbon?
Diamond.
Diamond, that's right. Diamond is made of carbon. It's very expensive, but it's just carbon atoms. Nitrogen, it's in our atmosphere. Right? In fact, over 70% of the air that we breathe are nitrogen. We can use it from the air directly. We breathe it in and then we just breathe it out. Right? About 21% of the air that we breathe is oxygen. And of course, we need oxygen to survive. Right? Hydrogen is explosive. Right? Uh, uh, um, Sometimes hydrogen can be used as a fuel. Okay. And phosphorus. Phosphorus is just a little bit of phosphorus in the body, and you can find them at the head of the match. It helps you light up the match. So these are the five key elements that makes up over 96% of our body. Well, what about the remaining 4%? The remaining 4% are made up of what's called trace elements. Trace elements are elements that we only need a little bit in our body. We don't want too much of it. Okay? Having too much of these trace elements will often lead to some kind of disease conditions. Not having enough is also going to cause a problem for us. So it's just the right amount. Okay? Deficiency means not having enough. Overdose means having too much. Both will probably end up with some kind of a disease condition. So examples of trace elements that you might be familiar with, including zinc. Zinc is needed for our defense system. We need calcium for our bones, but also for muscle contraction. Iodine is important for making hormones, and then magnesium as well. Do you have other examples of trace elements that you know? Maybe you take supplements for them. Maybe you have heard of them before. Let me know. Iron, exactly. Iron is another one. Iron is Fe. If you don't have enough iron, you might become anemic. Okay, you might have anemia, right? So that is that. I'm not sure what B is. Do you want to elaborate on that, Zara? Okay, moving on. Uh, Here are two examples of deficiency. Iodine deficiency can lead to goiter. Okay, so you have a gland here in the neck. It is called the thyroid gland. Thyroid gland. Okay? It makes hormones that helps you regulate metabolism. Right? So when people don't have enough iodine, the thyroid gland can get big, and it leads to this swollen gland here called a goiter. Right? This typically is not a concern for North America because where do we get our iodine? Where do you get your iodine? Does anybody know?
From the salt?
Hmm That's right. Our salts are iodinized. Okay, if you buy table salt from the supermarket, it contains iodine to prevent iodine deficiency. Right? Natural sources of iodine include seafood. They are pretty rich in iodine. Okay, but it's not something we worry about. Right? People can still get goiter for other reasons, but this is one of the reasons. Calcium deficiency, you probably know, will lead to osteoporosis. And osteoporosis is when the bone gets really brittle, easy to break because of excessive absorption of calcium from them. Right? If your body does not have enough calcium, they are going to take it from the bone. Okay, you need it for various functions, right, including muscle contraction. And if you take too much from the bone gets weak. Person gets osteoporosis. Okay, so five key elements that makes up over 96% of the body: carbon, hydrogen, nitrogen, oxygen, phosphorus. And then there are these trace elements that makes up the remaining four. Okay, not every single atom of the same element are necessarily identical to each other. We already know if we're talking about atoms of different elements, obviously they're going to be different. Carbon atoms are going to be different from nitrogen atoms, which are going to be different from oxygen atoms. However, even if you look at carbon atoms themselves, one carbon atom is not necessarily completely identical to another carbon atoms. Okay, it's possible for atoms of the same element to have different number of neutrons. Okay, remember, an atom is made up of three things: protons, neutrons, and electrons. Protons cannot change. All the atoms of the same element has the same number of protons. If you look at carbon, all the carbon atoms will have 6 protons. And you will learn how to count these things in chemistry. But the number of neutrons can be different. Okay? So if it has more neutrons, it makes it heavier. If it has less neutrons, it makes it lighter. These atoms with different number of neutrons, we call them isotopes. Isotopes. Okay, so I'm just going to give you some examples. Okay, most of the carbons that exist are what we call carbon 12. Carbon 12 has 6 protons and 6 neutrons. Don't worry about how you know. Like I said, you will learn it in chemistry. Okay? Carbon 13 also has 6 protons. Remember, protons do not change, but it has 7 neutrons. It's heavier. And then there are also carbon 14, which is 6 protons and 8 neutrons. Right? So they all have the same number of protons, but they might be heavier because of extra neutrons. Some of these isotopes, right, the heavier ones, they might be unstable. Right? When they're unstable, they tend to break down on its own. Right? So we call them radioactive isotopes because when they break down on its own, it's going to give off a little bit of radiation. So we call them radioactive isotopes. And with radiation, it means we can detect them. Okay, we can measure how much radiation is giving out from a sample, and then we would have an idea of how much carbon 14 is in it. And carbon 14 is used in carbon dating. Okay, carbon dating. If they dig up a fossil of some sort, doesn't have to be human, could be like like a mammoth or something, and they want to know how old it was when it died or how long ago did it die. They could check the amount of carbon 14 in it, and then they could do the math to figure it out. Okay. Iodine 131 is another isotope of iodine. I already told you your thyroid gland uses iodine to make hormones. Sometimes the thyroid gland can become cancerous, and you can give the person radioactive iodine because the thyroid gland is the only organ in the body that uses iodine. Any iodine that you consume will go to the thyroid. And so these radioactive iodine will go to the thyroid and then it breaks down and it gives off radiation. And the idea is that the radiation will kill the cancer cell. Okay? If you have a smoke detector at home, and you should, by law, you need to have one, there is a little bit of isotope in it. Okay, americium 241, and this isotope is key in component for a working smoke detector. Okay, that's why smoke detectors they have expiry date. They have expiry dates. Okay, once all the radioactive isotope breaks down, then it's not going to be functional anymore, and you're going to have to replace it. Okay? These radiations are very minimal. It's not like dangerous. It's not going to be causing you any health problems. So that's these are some examples of where you would use isotopes, um, in everyday situations. Okay. Does everybody understand isotope? Any questions? Okay. So atoms are the smallest unit of an element, and we know atoms are made up of, again, protons, neutrons, and electrons. Protons do not change, neutrons can change, and that creates isotopes. Number of electrons can also change. When an atom gain or lose electron or electrons, they become ions. They become ions. Okay. So there are positive ions. Right? If it gain, so gain electron, I'm just gonna do that for electron. If it gains electron, then it has extra negative charge, and it becomes negatively charged. Negative ion. If it lose electron or electrons, it can lose more than one, then it becomes positive ion. Okay. And we have a lot of these ions in our body, in the blood, for example. These ions are important because they form the electrolytes, right? And if you sweat a lot after working out, or if you have diarrhea, you're losing a lot of these electrolytes, and it could be dangerous. And that's why you need to replenish them. Okay. And Nadia is giving us a bunch of examples in the chat, which is very good. We have the potassium, we have calcium, magnesium, um, chloride. All these are important electrolytes that we need to have. When you're running low on electrolytes, you might experience a little bit of shakiness in the hand. You might have like shallow breathing. It's not good. Okay. So these electrolytes are ions. Ions are atoms that have either gain or lose electrons. Okay? So, smallest unit of an element is an atom, okay? Like hydrogen atom, oxygen atom. But we know atoms can actually come together and combine with each other in certain ratio to form something bigger. When we say H2O, it is actually two hydrogen atoms connected with one oxygen atom. Okay, and this ratio, this 2-to-1 ratio is fixed. All the water that we know of is made up of H2O. It doesn't matter if it's water from your tap, water you scoop up from the ocean, okay? They are all H2O. It's a fixed proportion, right? If it has an extra oxygen, then it's no longer water. Right? H2O2, that's hydrogen peroxide. What do we use hydrogen peroxide for? Usually comes in a brown bottle and you buy it from the store. What do we use that for? No, nobody has hydrogen peroxide at home.
It is using for dressing.
For dressing, yeah, like a wound, right? Is that what you mean? Yeah, it's for disinfection, like exactly. Okay, so you can drink this stuff, okay, but you can drink water. Right? What is this? Toxic? Look, I mean, you shouldn't drink it, but like, it's not a poison. Okay, you can apply it to your wound, and it's gonna disinfect. It's gonna help you clean the wound, basically. Okay. All right, so atoms can combine to form in fixed proportion to form molecule. So this is a water molecule. You're not gonna find these molecules on the periodic table because it's actually multiple things coming together, right? So for example, here we have sodium. Sodium is an element. If you look it up on the periodic table, it's Na. Okay, sodium is a metal, but it's not what you think. Right? Like when we imagine metal, we think of something like hard and shiny and very strong, right? But sodium, even though it's a metal, it's actually very soft. You can cut it with a butter knife, and it's really reactive with moisture and water. If you have a chunk of sodium the size like this, and you drop it into a bucket of water, it will literally blow up. Okay, you can Google it and watch a video on YouTube. They have people doing this online. So that's why they're wearing gloves because the moisture on the hand can set off the sodium, right? So this is very dangerous. You don't want to be keeping sodium around you, right? We have chlorine here. Chlorine, if you look it up, is Cl. And chlorine is also very, very poisonous. Okay, dangerous. Right? Chlorine gas is used to make mustard gas in World War II. And if a person inhales these gas, it will destroy the lining of your lungs and you die. Right? So again, not something you would want to keep around your house. And then something interesting happens when these two things come together chemically. When you connect sodium with chlorine together, you get sodium chloride. Okay, so individually they are elements because you can find them on the periodic table, but once you put them together, they become a compound. Okay, a compound, and this is sodium chloride. It is table salt. Table salt. Right? So if you look at the molecules that make up the sodium chloride, it's 1 part sodium and 1 part chlorine. And table salt, of course, is neither explosive or poisonous. We put it on our fries. Right? So the point I'm trying to make here is when you combine elements together to form a compound, the properties of the compound that you get in the end are very different from the individual element. Do you understand?
How
Now,
they compound this?
I'm sorry, I missed that one more time.
How they compound this?
How do they combine this?
Yes.
Yeah, okay, so like if you drop sodium into chlorine, they will automatically react and form sodium chloride. But we don't have to worry about making sodium chloride this way, okay? Because in in practice, people get the salt by mining them, right? Okay, so they can mine it from ocean water, right? Seawater, right? Evaporating them, and you're left behind with the salt. So nature already made them, but you can artificially make more of them, right? By putting the sodium in the chlorine. Do we have another question? Now, there is a misconception I want to address, okay? After looking at this, people sometimes get really confused. They're like, I don't understand because don't we have sodium in like the chips or something, right? People say cut down your sodium, right? But like, why are we eating this stuff if it's so explosive? Or people would think, oh, there's chlorine in the pool, right? And isn't it dangerous? Because chlorine, I just told you, is poisonous. So when people use these terms in everyday conversation, they're not exactly thinking about chemistry per se. Right? So when people say there's sodium in your food, what they are really saying is they are actually talking about sodium chloride. Okay, again, if people haven't taken chemistry or if they've forgotten all the chem they took in high school, then they might not know the difference, right? Okay, so when we use these words in everyday language, we are not necessarily talking about the elemental sodium. It's the sodium, in a compound form. Similarly, when we say there are chlorine in the pool, we're not saying there are chlorine gas in the pool. That would be extremely dangerous. Okay. We are saying there are chlorine containing compounds in the pool, namely bleach. Bleach contains chlorine. Okay. It's a compound that has chlorine atoms in it. right? And as I told you, the compound that you get in the end is not necessarily going to have the same um, properties as the individual elements. Okay. Yeah, even on the nutrient tables, they say sodium and not the full name. Exactly. Right. But I'm telling you, that's what it means. Okay. When you read the label, it says sodium, it doesn't mean the thing's gonna blow up. It just means it contains sodium containing compounds. Bottom line, do you understand the difference between elements, excuse me, element and compounds
Yes.
and atoms and molecules? Thank you.
It was very clear because I was about to confuse why it's so dangerous and why we are eating, but thank you so much. It was very clear.
Thank you. Thank you. Okay. Anyone else have any questions?
Yeah,
Should be
so sodium and chlorine has a chemical bond, and after that, sodium chloride. This is compound, and we can eat. We can eat this one, but element we cannot eat,
that's right.
and
In this
because
case.
this is maybe poisons.
That's right. Okay. So
Yes.
the point is that individual, you can think of the elements as Lego blocks. Okay. So we have the blue Lego blocks, we have the red Lego blocks, and they are on their own, but we can put them together. Once we put these things together, you get a compound. Okay. That's the key thing to understand. Right?
And chemical compound has a chemical bond.
Exactly, right? It's a chemical bond, which is what we're going to talk about in the next slide, are basically glue that holds these atoms together. Okay? All right, moving on. Feel free to drop questions in the chat if you have any. So, how do atoms stay together in a compound, in a molecule, right? Well, there are chemical glues that hold them together, and there are two kinds of glue. And I'm just giving you an overview of this stuff, right? You're going to learn much more about this thing in your chemistry class. Right? But for now, we have ionic glue or covalent glue. Okay? Let's see what the difference are. In ionic bond, what happens is there is a transfer of electron, okay? Or more than one is possible as well. For a reason we're not going to go into, because you will learn it in more detail in chemistry, metals tend to want to give away electrons. Okay, so sodium is a metal, it wants to give away an electron. Whereas chlorine, being a non-metal, they tend to pick up electrons. So they are a perfect match. Okay? Sodium wants to give it away, chlorine wants to pick it up. When they come together, they're like, let's form a partnership, let's form a bond, and we get sodium chloride. Okay? So that's pretty much how a lot of these compounds are formed. It involves the transfer of electron from one atom to another. But that's not the only way to glue atoms together. Right? We can have covalent bond. A covalent bond involves the sharing of electron or electrons, right? So they are not, it's not like one atom give it to the other one. It's more like, let's share it together. Okay. I will contribute one electron, you can contribute the other one, and we will share them together. Okay? So sodium chloride is an example of ionic compound that involves transfer of electron. Water is an example of a covalent compound because they are sharing electrons. Okay, so if they have an ionic bond, we call them ionic compound. If they have a covalent bond, then we call them a covalent molecule. Okay, so we now understand what molecules are. They are basically, when you put elements together, we put atoms of different elements together in certain ratio, you end up getting a molecule, right? Some molecules are organic, others are not. The definition of organic in chemistry and biology, for that matter, is very different from like organic food. Okay, when you describe something that's organic food, it means it's raised without, pesticides and stuff like that, right? But in the context of what we are talking about, a molecule is organic if it contains carbon atoms. Okay? Many biologically important molecules are organic. Okay? So glucose is very important for us. Okay? We burn glucose for fuels. Okay, and that is C6H12O6. Okay, C6H12O6. You don't have to memorize it now. We're gonna learn a lot more about glucose later on, and you will memorize this eventually. So that's an organic molecule because it has carbon in it. Proteins also have carbon in it. Not all organic molecules are necessarily related to a living organism. There are a lot of organic molecules that we use in other stuff, right? Polyester, like if you windbreaker, right, the surface, it's probably made of some kind of like polyester. That is an organic molecule. Methane gas, which is like greenhouse gas, that's organic. If you cook with non-stick pans, right, the black stuff, that's called Teflon, right? That's uh, that's an organic molecule. Okay, so organic doesn't necessarily mean it's in a living thing, and it doesn't even necessarily mean it's good. Okay, in fact, the Teflon is quite bad for your body. Organic, in the context of our discussion, just means they have carbon atoms. All right. Now there are three exceptions. The people who made up these rules, they decided that carbon monoxide, carbon dioxide, and this thing is called cyanide. These things, even though they contain, oops, sorry, spelled that wrong. Cyanide, even though they contain carbon atom, we don't consider them as organic. Okay, so there's just some exception there. Questions?
So we say organic because it has oxygen, no, sorry, carbon atoms in it, right? That's why.
That's right. Mhm. Good. All right, let's take a closer look at water. Okay, closer look at water. Water molecules are special uh, because of its unique property. Okay, actually, maybe not unique, but it's like it has properties that makes it compatible with life. Okay, so let's do a quick note here to understand what I mean by that. Okay. Water molecule. So usually how they draw water molecule, it's like Mickey Mouse, right? Mickey Mouse, the ears. Right? This the face of the Mickey Mouse. That's where the oxygen is, and then the ears, that's where the hydrogens are. H2O, right? Two hydrogen, one oxygen. And then if you were paying attention, you would know the hydrogen and the oxygen, they are sharing electrons. They're sharing electrons. But when you say share, it implies, 50-50, right? It's like when I get a toy for my kids, I'm like, please share. But what ends up happening most of the time is one of them is gonna hog the toy and they're gonna be playing with it more often than the other. So even though they're sharing, but one gets to use it more often. And that's what's happening here. Okay. Again, for reason you will learn in chemistry class, um, oxygen tends to be hogging the electron a little bit more. So this sharing of electron, it's uneven, okay? Uneven sharing of electrons. The oxygen will pull the electrons towards itself more stronger than the hydrogen is able to do so. And as a result of this, the oxygen portion is slightly negative. Slightly negative. Okay, we have a symbol for it. It's like an 8 that you don't finish drawing and then negative. Okay, if you see this symbol, it means slightly negative. And by the same logic, the hydrogens would be slightly positive. Overall, though, the molecule is still neutral. Right? The number of protons and electrons are still the same, but because of the uneven sharing, the distribution of the electrons are a little bit concentrated on one side. So that makes the molecule polar. Okay? Polar. Polar means one side is more negative than the other. So that creates an interesting property. Let's draw another water molecule here, another Mickey Mouse. So over here, the O is slightly negative for the same reason. Here we have slightly positive. And so when two water molecules are brought next to each other, they are attracted to each other. The slightly positive hydrogen is attracted to the slightly negative oxygen, right? They are like tiny magnets that are attracted to each other. And this attraction is called a hydrogen bond. Okay, we will hear this hydrogen bond thing coming back again and again throughout the course. Okay? Don't make it too complicated. Anytime you see hydrogen bond being mentioned, it just means there is an attraction between molecules. Okay? They're attracted to each other because one part is slightly positive, one part slightly negative, and then they would stick together like a magnet. Okay? Questions? Don't worry, we'll have a break today. Okay? Unlike Monday, I'll give you a break today. So in this picture, you can see the red portion is the oxygen, and then the white portion is the hydrogen, and then they are always attracted to each other. So there's a hydrogen bond here, hydrogen bond here, hydrogen bond. And basically, all the water molecules are clinging onto each other. Okay. And it forms like a film, right? You know those bugs that can walk on water? They're called water striders. They can walk on water because of this property. Water forms the film, right? If the bug spreads its way evenly, it's not going to break through. This is the reason why we can suck water up a straw. Right? When you suck up one water molecule, the attraction to the next one will pull the next one up and the next one up, and then the whole chain goes up the straw. Right? So polar molecule. One part is slightly negative, the other part is slightly positive, and it's caused by uneven distribution of electrons, and they behave like tiny magnets.
I have a question. So the hydrogen bond is happening only in water or in something else also?
Yeah, so in other molecules, it's also possible to have this hydrogen bond, right? And we'll mention it as we go through the examples. But for now, water would be an easy example to understand what it means.
All
Okay.
right.
Again, it's just what the positive part is subtracted to the negative part between two molecules. So
And
water, sorry, go
sorry,
ahead. Yeah, go
I
ahead.
have another question.
Yeah.
So you know the energy we say negative energy and positive energy around us. Is it related to this?
No, no, no.
It's
Absolutely
not.
not. Yeah, yeah, yeah.
All
Good
right.
question though. Yeah. Okay. Water is an excellent solvent. Okay. A solvent is something, it's usually liquid that is able to dissolve other things. If you think about one of these, what do you call that? A fruit punch package. Right? It comes in a little powder, and then you can mix it with the water, and then you get the fruit punch, right? So this here, the solid, that the powder, that's the solute. The water is the solvent. And then in the end, you get a solution. Okay. So water is a good solvent because it's able to dissolve a lot of things. All those ions, all those electrolytes that we mentioned that are important in our body, they are basically solute that has been dissolved in water, and it's, part of our blood. Right? So water is a good solvent. Not everything can be dissolved in water, but a lot of things can. If it can dissolve in water, if you are able to dissolve it in water, we would say it is hydrophilic. Hydro means water. Philic means loving. A hydrophilic molecule is a molecule that loves water and it's going to be able to dissolve in it. An example would be salt, okay, table salt. Okay, table salt is hydrophilic. Remember, salt is made up of Na and Cl, and I told you Na likes to give away electron, so it becomes positive. Chlorine likes to receive electrons, so it becomes negative. And when you put it in water, basically, the chlorine being negative will be surrounded by the hydrogen portion of the water, whereas the sodium being positive will be surrounded by the oxygen portion of water. Maybe it's difficult to see in this picture. Let me just quickly draw it for you. Okay, this is Na plus, right? Remember, water has two parts. It has the water, that's the oxygen portion, and the hydrogen portion. The oxygen is slightly negative, so it makes perfect sense for the oxygen to be hugging around the sodium. On the other hand, if you have the chlorine, which is negative, the hydrogen will be hugging the chlorine now. Right? So this interaction essentially allows the salt to temporarily separate, not back into sodium atoms and chlorine atoms, but separate into its ion form. Okay, and that allows it to dissolve into the water. Okay, can I have some other examples of hydrophilic molecules besides salt? What else is hydrophilic? Something in your kitchen, okay? Nothing fancy. I got a message here. Sugar, that's good. Sugar is hydrophilic. What else? What else in your kitchen is hydrophilic? Two more. Give me two more things that can dissolve in water. Okay. Baking soda, good. One more. Anything? Like, I mean, like you must have mixed things with water every day, right? Like, as part of cooking or, for other reasons. What goes into the water and it mixes well and it dissolves? Yes, thank you. Okay, there's vinegar. That's what I'm looking for. Someone else say hot chocolate powder. Absolutely, right? Cornstarch, right? All these things can go into water. Honey, there we go. Okay, all these things are hydrophilic because they can dissolve in water. Now,
Glucose.
huh? Sorry?
Glucose.
Yeah, glucose, absolutely. Although we don't have glucose in the kitchen, right? Like people don't really buy glucose. Um, I mean, you certainly can, but most people just have like regular kitchen sugar, right? And that is not glucose. But I get your point. Okay, give me something that is not going to dissolve in water. This is easy. You must know these two things don't mix together. That's right, oil, right? Oil. So oil and other things that cannot dissolve in water, we call them hydrophobic molecules. Hydro is water, phobic, as in like phobia, it's to be afraid of something. So these molecules are hydrophobic, they're afraid of water. Usually they are non-polar molecules. Okay? So unlike polar stuff, right? Because water is polar, so anything that's polar will be able to dissolve in water, but anything that's non-polar will not be able to dissolve in water. So what does it mean by non-polar? Non-polar basically means instead of uneven sharing of electrons, they actually share evenly. Okay? So no one's hogging the electrons. These are good kids. They will share the electrons 50-50. Okay? You get to use it Monday, Wednesday, Friday. I will use it Tuesday, Thursday, and Saturday. And nobody touches it on Sunday, right? It's like even sharing, right? Non-polar. Non-polar stuff are hydrophobic. They do not mix well with water. Besides oil, what else don't mix with water? Doesn't have to be something that you eat, okay? That you consume. Can you think of another example or something? Yeah, I guess sand, yeah, sand, sure. Although we wouldn't really say sand is hydrophobic. It's true, it doesn't dissolve in water, but it's not quite right description. It's like, if I put my mouse into the water, it's not gonna dissolve, but I'm not gonna say the mouse is hydrophobic, right? Like, it's not really the right description. Okay. Thinking about like wax, for example, wax. Right? If you drop hot wax in the water, it will just float to the top. It's not gonna mix, right? So that's another example right here. Okay, not honey though. Honey can dissolve in water. Okay. In fact, that's how most people drink honey, right? Dissolve it in a little bit of tea or water, and then you drink it, right? All right. We good?
Yes.
Yeah, thank you. We're almost done, guys. Okay, with the chemistry stuff. We're gonna start biology soon, finally. Okay. Just let me know if you have questions, please. Don't be afraid to ask. pH scale. pH scale. Yeah, so pH scale is something that is being used to determine the acidity of a solution. Okay. If it's 7, then it's neutral. So pure water is neutral. Okay, not the tap water. Tap water is not pure. Tap water has a lot of like minerals dissolved in it, okay? Contaminants too. Okay, so it's not actually 7, but if it's pure water, okay, if you distill it and you extract it, then it's gonna be 7. Anything that's below 7 here, that's gonna be acidic. So think of like citrusy stuff, lemon juice, orange juice. You have acid in your stomach, all that stuff is going to be acidic. Vinegar is acidic. They usually taste sour. They're corrosive. Okay. On the other hand of the spectrum, if it's above 7, then we say it is basic. Oh my goodness, can't spell today. Basic. Okay, basic. Right, so think cleaning product. Most of the cleaning products are basic. Baking soda, ammonia, bleach, all those things are basic. Okay. If you have really bad heartburn, which means you have too much acid in the stomach, then you take Tums. Okay, Tums are basic. It will neutralize it and make you feel better. Okay, there's a question. Is this what people mean when they talking about balancing their pH? Yeah, I hear these commercials all the time saying there are these like alkaline water, right? That's supposed to make you healthier. I think it's just a gimmick, okay? It's mostly placebo. It's not good science, right? But yes, that's what they're talking about. Right? In fact, you're not encouraged to drinking water is the best way to rehydrate. Okay, I know a lot of people think, drinking the coconut water or drinking these alkaline water or these um what do you call those things where you can infuse the flavor into it? Sparkling water, yeah. Like they think that is going to be better for restoring the electrolytes, but pure water is the best. Okay, oh, not pure water, just like regular water. Okay, where the pH is very close to 7, and that's what your body naturally needs. Okay. Anything that they sell you with like high pH, low pH, whatever, it's just gimmicks, in my opinion. All right. Our normal blood pH is about 7.35 to 7.45. So a little bit on the basic side. Okay. And we need to keep it within this narrow range. If it's too high or too low, then we're going to have a problem. Okay. Anything less than 7.35, it's too much acid. We call it acidosis. Acidosis. Don't worry about these names. Okay. I'm just showing you. If it's greater than 7.45, then it's alkalosis. It's too much base. Alkalosis. And acidosis and alkalosis, if not dealt with quick enough, it could be quite dangerous. Okay. There are various systems within the blood that helps you balance the pH, and your respiratory system and your kidneys can help with that. But if these things fails and it does fall outside of these range, then a person could have a life-threatening condition. Okay. They could, slip into a coma and all sorts of problem will happen. That is it for the chemistry. Okay, let's do polls and then we will do the biology. Okay, let's see if you were paying attention. All right, just a couple more seconds. Okay, thank you very much. Water is polar because of one side being more negative than the other, and that is because of uneven sharing of electrons. Okay, so the answer is C, uneven distribution, uneven sharing of electrons. C. Okay, so that's that. Next one. Now we're gonna switch to the biology. Okay, we're gonna switch to the actual application of macromolecules in the context of a living organism. Okay, so let's start with looking at the key macromolecules. Okay, the key macromolecules that we have in our body include carbohydrates, people call them carbs, proteins, which you can get by eating meats. If you are vegan, then you can get it from soy product, for example. Lipids, which is kind of like your uh, oily stuff, and nucleic acids, which is what our DNA are made up of. Looking at the time, probably we can do carbohydrates today, and that's it. Okay, may be a little bit limited. I don't know. I'd rather not start on something that I cannot finish. Okay, we'll see. Okay, a little bit of background information first, and then we're gonna talk about carbohydrates. 4 hours of chemistry? What do you mean? I thought you guys only had 2 hours this morning. You guys have 4 hours?
No, it
Now
was
it is
3 hours
3 hours.
and it was very heavy.
Oh, really? 3 hours? Oh boy.
Yeah.
Yeah, yeah. Well, welcome to the pre-health program, guys. Woohoo! So let's keep going. Macromolecules are collectively known as polymers. Okay, polymers. Polymers are basically long chains of the same thing repeating over and over again. There's like little building blocks that we connect together. Okay, so I'm gonna try to draw this out for you to help you understand. Okay, we have over here m- monomers, monomers, and polymers. Okay, here we go. Here we go. After this, I'll give you a break. Okay, looks like you guys need one. So monomers are individual building blocks. Okay, so think of them as like little beads. Like when you put beads together to make a necklace or something like that, right? These are individual building blocks, and we call them monomers. Monomers. Okay, building blocks. Think of them as individual carts in a train. And then we can hook them up together. We can join them together chemically. Can join them together chemically, and we will have a chain. There you go. So this chain, which can be longer, but I'm not going to draw too many of them, it is called a polymer. Polymer, okay, a chain. Okay, you already know some polymers in everyday life. Okay, we mentioned about polyester, right? Plastic is polyethylene in some cases, right? A lot of the stuff that we use every day, it's long chains of these repeating units. So the macromolecules that we are studying is no different. They are also polymers. Polymers. Okay, so we can join them together. And the chemical process that we use to join them together in the body, it is called dehydration synthesis. Okay. Synthesis means to create. Dehydration means to remove water, right? So to connect these individual building blocks together, we need to remove H2O. Okay. I am terribly sorry, but there are other names for this as well, and I'm just writing it out for you in case you come across it. Condensation reaction. And you think about condensation in the on the window, you see the water coming out, right, out of the air, right? That's basically what it is. You're removing the water from it. Now, when
Remove the water. Sorry.
yeah,
Why
re
we remove water?
okay, we'll talk about the why after the break. Keep that in mind. It will make more sense when I show you the actual molecule. But as a general rule, anytime you want to connect these building blocks together, anytime you want to form a bond, you need to remove water molecule. The opposite can happen. when we eat our starch, when we eat our carbs from pasta, bread, rice, what have you, our body needs to digest them. We need to break the polymers back into their individual building blocks so we can absorb the nutrient and use it for something else. So the opposite of this is called hydrolysis. Hydrolysis. Okay, I've been repeating this a couple times, so you should know by now. Hydro means water. Lysis is to break. So hydrolysis is to break the bonds by adding water. Okay, so if you want to connect them together, you need to remove water. To separate them, you need to add water. Okay, and that's how you build polymers and how you break polymers. Okay, so I'll leave it on this screen and then we will continue when we come back. Oh, it's 5 minutes. If it makes you feel any better, I had a 3-hour class this morning as well. Okay, so we're in the same boat, guys. Let's take 5 minutes and then we will continue when we come back. See you soon. Hello, break's over. It's me again. Let's keep going. So now you kind of understand the relationship between, how we put these building blocks together and how we break them apart. Let's take a look at actual examples to help you get a better understanding of it. Okay. So first of all, there is a table here that summarizes the names of the polymers that you get for each type of macromolecules, as well as the kind of building blocks that we need. Don't worry about it at the moment. As we go through our lessons, we will learn them slowly, one at a time. Okay. Don't worry about what the hexagon means at the moment. I will explain later. I can't explain everything at the same time. It's just going to be too overwhelming. I'm sure it's already overwhelming with all these new informations, okay? But just, take a step of faith here. Don't worry about the hexagon, whatever it means. Forget it for now. The focus would be on the OH right here. Okay, so here we have one monomer. This is a monomer. And then here we have another monomer. Okay, think of these as those little red circles that I drew. And I want to connect them together. So what is the name of the reaction? Well, it is dehydration synthesis, or you can also call it condensation reaction. In this reaction, you need to remove a water molecule. So how do you do that? Well, you can take an OH from one of these things, and then you can take an H from the other one. Okay? And then so the H2O will come out, and you will have the water. And the remaining stuff you can connect together with a bond. Okay, so these lines, they are basically a bond that shows the covalent bond, okay, the sharing of electron. And now the two things are glued together. It's not a polymer yet because you only have two of them, but you can repeat the process again and again and again. And eventually you can grow the chain and it becomes very long. Then we have a polymer. What if you want to break it apart? Okay. Again, we have only two things here for simplification. But if you want to break it, then you have to use hydrolysis, water to break. That's what it means. So the water molecule, we will take the H from the water and put it back on one of them, and then you put the OH back on the other one, and you will be able to separate the two. Okay? So that's the relationship between forming the bonds and breaking the bonds. Let's take a look at this question. Okay. There are two monomers here. We have one that looks like a hexagon, which I'll explain what it means later. There's one that looks like a pentagon. And if we want to join them together, what would be the product? Okay, please choose one of the answers. Okay, just a little longer. I'm gonna close the poll soon, so pick something if you can. Okay, there we go. Thank you for those of you who have answered. Remember, when we try to join these things together, we are going to be removing an OH from one and removing an H from the other. It doesn't matter which one you choose. Let's say you remove OH here and you remove the H, and then you'll be able to connect them together. So we're going to have a hexagon connected to the O and then to the pentagon. So the only one that matched that description is this one. Okay. Some people chose A, but don't forget you are taking just a water out, H2O. There's going to be an O in the middle. Okay. It's not going to be C because if you pay closer attention, you can see both of them are pentagon, and these are both hexagon. It's one hexagon and one pentagon. Does anybody have any question about this? For those of you who did not choose anything, do you understand why the answer is B now? If not, ask.
I have a question.
Sure, please.
Are we going to have more questions, practice questions for this?
Well, you're not going to have to draw anything on the test, but if I give you something similar like this, you should be able to do it. Why don't we just do another one since you asked? Um, do you mean practice question for this one particularly or like in general?
That one particularly.
Okay, sure. Let's do one. Okay, let's say we have a square here, and then we will draw a triangle, okay, with an OH. Let's say you want to put them together. Okay, let's think about what the result will look like. Okay, I'm just going to give you guys a minute to draw it out, and then I will show you the answer. Okay, hopefully you have something that looks like this. You're gonna have the square, and then the O, and then the triangle, right? And the reason for this is because in dehydration synthesis, you're gonna remove OH from one of them, and then remove H from the other, and then don't forget you still have an O that's gonna be linking them together. Is that a little bit better, or you have a follow-up question? Was it Natalie? I think it was Natalie, right?
Yeah, it's much clearer. Thank you.
Okay, thank you. All right. Oh, another thing I want to talk about here. Let's backtrack for a second. So we have 8 of these monomers together. 1, 2, 3, 4, 5, 6, 7, 8, and I joined them all together. I want to ask you, how many water molecules do we need to remove in order to join them together? I'll give you some answers and you have to tell me. Is it 5, 6, 7, 8, or 9? Oh my goodness, I don't know my ABC. There we go. Let me launch the poll again.
Can you repeat the question?
Yep, the question is, if I want to connect all these building blocks together, if I want to connect all these monomers together, how many water molecules do we need to remove in order to join them together? These questions I'm asking you might show up on your quiz, okay? I cannot guarantee it's going to show up in your quiz because it's like a whole pool of questions. I don't know which one gonna get, but these type of questions are in the pool. So make sure you know how to answer them. Okay, even if you're not sure, choose something. Okay, guess. Okay, we'll leave it at that. The answer is, let's see. If I want to join this one with this one, then I have to create a bond, right? Every time I create a bond, I need to remove a water molecule. So that's 1 water molecule, 2, 3, 4, 5, 6, 7. Okay? The correct answer is 7. Okay? 7. Every time you connect 2 together, you need to take away a water. If there are 8 things that you want to chain together, you need to make 7 connections, which means you need to remove 7 water molecules. Okay?
Yes.
Mhm. All right. Finally, carbohydrates. Here we go. Okay, carbohydrates. As I go through the macromolecules, there are a couple things I want you to keep in mind. I want you to think about what the elements are, what kind of atoms are in the macromolecules. I want you to think about the function, the monomers, as well as the structure associated with these macromolecules. Okay. Don't worry if you didn't catch all that. I'll write down for you when we get there. So first of all, carbohydrates. Carbohydrates are organic. What does organic mean again in this context?
When it has carbon in it.
Exactly, right? So it's an organic molecules and it always contains carbon, hydrogen, and oxygen. The ratio of carbon and H2O is always 1 to 1. Okay? That's why it's called carbohydrates. Carbo is referring to the carbon, hydrate is referring to the water. So let's say N equals to 6, right? Then it's going to be C6H12 because 6 times 2 is 12, O6. Okay, so this is glucose. You can have other N numbers. Okay, you can have N equals to 12, then it's C12H24, O12. Okay? What's important is to understand the ratio between carbon and water is always 1 to 1. What do we need carbohydrates for? Well, carbohydrates has a lot of biological functions depending on what organism you are talking about. For humans and other living things, we use carbohydrates as a quick way to produce cellular energy. Okay? Everything you do in the body pretty much requires energy. Okay, to understand what I'm saying to you, to write down the notes for the beating of the heart, breathing, all these things need energy. And to sustain these energy requirements, we burn carbohydrates in our cells. For some organisms, like plants and some shelled animals, they need carbohydrates for structural components. Okay? The shell is made up of a type of carbohydrates called chitin. It has, other stuff in the shell as well, like calcium, for example, but it contains some carbohydrates as well. We humans do not use carbohydrates for structural components. Okay. None of the structures in our body is made of carbohydrates. We primarily use it for um, energy, okay, for producing energies. Plants, they are crunchy. The crunchy parts of the plants are made up of, again, a type of carbohydrates. How do we burn the carbohydrates? We do it in a process called cellular respiration. Don't worry about memorizing this yet. Okay, we have a whole lecture dedicated to cellular respiration later on. Okay, it's lecture 5. But I just give you a foreshadow, okay, like a little overview here, so you will start to recognize the formula. We take glucose in the cell and we react it with the oxygen that we breathe. In the process, it creates carbon dioxide that we breathe out, as well as water. But most importantly, this process produces energy. Energy. And this energy is going to be useful for fueling everything that we do. All right? Cellular respiration. We are not the only thing that does this. Right? Every living thing pretty much does some version of this. Okay, plants, they do this for sure as well, right? Other animals. Where do we get our carbohydrates? Well, there is certainly no shortage of carbohydrates in Western diets. Okay. We get our starch from rice, corn, wheat, potato, yam, cassava, pasta. All these things are very rich in starch. In addition, we also get other sources of carbohydrates, such as fruits and corn syrup, maybe. If you add a little bit of syrup on your pancakes, that's a lot of fructose in there. Okay. The fructose in fruits are reasonably healthy. Right? They are healthy, I would say. But if you look at processed food, they have what's called like high fructose corn syrup. That's like the processed stuff, and it's not too good for you. Okay. Lactose is found in dairy product like milk. What else? Where else do you find lactose besides milk? What other dairy product?
Cheese.
Cheese, yeah. Ice cream, yogurt, right? All those things are going to have lactose in it. Some people are lactose intolerant. They can't take these things. Sucrose is regular table sugar. It's the stuff in your kitchen, and boy, it's everywhere in everything that we eat, basically. Okay, a lot of the stuff that we eat. Okay, candy bars, peanut butter, jam, orange juice, all these things are packed with sucrose. Okay, if you look at a can of Coca-Cola, it has like 34 grams of sugar in it. Okay, the sugar that they're talking about, that's sucrose. Okay, so lots of sources of carbohydrates. Not all of them are good carbohydrates, of course, but it's not something that we need to um, completely cut out. Right? In fact, we need carbohydrates to survive. Structure of carbohydrates. Right? So the building blocks that makes up carbohydrates are the following: glucose, right, which is the stuff that we burn; fructose, which again, something that you can get from the fruits naturally; and something called galactose. Galactose is not the same as lactose, okay? So these are the individual building blocks, and they look like this, okay? No one's going to ask you to draw them. I'm not going to ask you to identify them, but you can see the structure of the glucose is basically a hexagon shape, right? So that's what this thing was, right? This was basically a glucose molecule. And then we have another glucose molecule, and we want to join them together, right, to create something bigger. Okay? If you look at the fructose here, it's a pentagon, right? Galactose is another hexagon. So these are all the building blocks for different kinds of carbohydrates. Okay. And they are just single sugar, and we have a fancy name for it. Okay. Single is mono. Mono is one. Okay. And then saccharide is sugar. So these are single sugar, monosaccharides. Okay, so please remember the monosaccharides: glucose, fructose, galactose. Okay, these are the individual building blocks, the little red circles that we're going to join together to form the polymer. Okay, single sugar. So they are single and they are ready to mingle. If you put a glucose and a fructose together, they can join chemically. And you can see over here the hexagon and then another and the pentagon right here. You can remove the water molecule, take away the H and the OH, and then they will form a bond that glues them together. In the process, you will remove water molecule. So the glucose plus the fructose will now give you sucrose. If you remember from earlier, sucrose is kitchen sugar. That's the stuff you have in your cabinet. Okay. So when you consume sugar, if you just like take a spoon of sugar or something, or eat some candy, you are consuming sucrose. And your body will break it back down into glucose and fructose. How does it break it back down? Remember, if they are stuck together and you want to break it apart, you got to add a water molecule and it will separate them back into its individual component. Okay? So when you eat the candy, when you get the sucrose, your body breaks it back down to glucose and fructose. This you can then go burn it in cellular respiration and it gives you energy. And this is a relatively fast process. That's why sometimes like in class, if you're like sleepy and then you pop some candies in your mouth and then you might feel a surge of energy, right? For a little bit. It's not like very sustainable. Does that make sense? So
Yeah.
these things are double sugar, right? Because they're two things stuck together. We call them disaccharide. Okay. Monosaccharides, single sugar. If you put them together, you get disaccharide. There are different types of combinations, as you can imagine. Okay. And these are the ones that I want you to know. Okay. If you can't remember them, then put it on the help sheet. Okay, put it on the cheat sheet. Put it next to you on the test. It's fine. Okay, I told you already. For my course, you are allowed to do that. Glucose plus glucose gives you maltose. If you look at the candy bar ingredient, you will almost always find maltose in it. Okay. Glucose plus galactose gives you lactose. That's the stuff that you will find in dairy products like ice cream. Glucose plus fructose will give you sucrose. We already talked about that, your kitchen sugar. Okay. So on the left side here, once again, these are monosaccharide. And over here, these are disaccharide. Okay. And you have to remove a water molecule to connect them together. Okay. Any questions? Almost there. Hang in there. So lactose intolerant is a condition where a person is not able to digest the lactose, right? And instead, the bacteria in the guts are gonna basically feast on the lactose. Since you're not breaking it down, they're like, okay, let's eat it for them. And as a result, it produces a lot of gas and bloating, and they might give you diarrhea, right? Uh, so people who are lactose intolerant, they are usually missing the thing in the body to break down the lactose, and you can take that missing thing as a tablet. Okay? The thing that's missing is called lactase. We'll learn more about enzymes next class, but You can take one of these things before you enjoy your Sundays, and it's going to be okay. Right? So that's lactose intolerant. So monosaccharide, single sugar, disaccharides, double sugar, but don't stop there. We're trying to build a long chain, right? So we keep on connecting more and more and more and more. Eventually, you're going to get a long polymer, and we call that polysaccharides. Polysaccharides. Polysaccharides can be straight, so it's just like, you know, glucose connected to a glucose connected to a glucose, so on and so forth. Okay. Or it could be branched, as in, you get your main branch here. These are all glucose, and then it will come off and has another side branch. Okay, it's possible the side branch has more side branch as well, right? Depending on which molecule you're looking at. So they could be straight, okay, or branched many times. And there could be hundreds and thousands of glucose in it. I'm going to go through a few common polysaccharides with you: cellulose, glycogen, and starch. These are all polymers that are made up of just glucose. Okay? They are glucose connected together, but in different configuration. Okay? For example, like if I give the whole class a box of just yellow Lego blocks, okay, just yellow Lego blocks like this, okay, you guys can build anything with it, right? Like some of you might decide to build something very long, some of you might decide to build a block, right? It's kind of like this. The glucose is the building blocks. Depending on how you link them together, you will end up having cellulose, glycogen, or starch. Okay? It's all about how you link them together. Let's start with cellulose. Cellulose is very strong, okay? Very strong, very tough. Okay? They are used to make the fibers in the plants. Okay? We will learn more about cells later, but if this is a plant cell, the plant cell is going to have a wall around it to give it extra protection. Okay? This cell wall is made up of cellulose, and that's the fibers of the plant. Okay? When we eat our vegetables, we also consume the fibers. We consume the cellulose. However, we cannot digest cellulose. We don't have the enzyme. We don't have the ability to break it down. So cellulose just kind of moves through our digestive tract and it helps us go to the bathroom. Okay? So dietary fibers is important to give us good health, but it doesn't give us any energy. Okay. Um, Cows and other grazing animals, they of course eat grass most of the time, and there are a lot of fibers in grass. They actually rely on a special kind of bacteria that's living in their guts to help them break down the fibers. Okay, and if you look at a cow, they are chewing all the time. Do you know cow has more than one stomach? How many do they have? Anybody?
4.
Mm-hmm. So the cow actually has to swallow the food and then they digest it a little bit and then they burp it back out and then they have to chew some more and then it goes back down and then it goes into second stage of digestion and it just keeps on doing this regurgitation and swallowing throughout the day in order to break down these cellulose. Okay, fun fact, every time they burp, they actually burp out a lot of methane gas. And cattle's, especially because we raise them for food, cattle is the burp that they produce is one of the major contributing source of greenhouse gas. Okay, and that's why eating beef is not environmentally friendly. Okay, so that's cellulose. Okay, it's indigestible in humans. It just helps our digestive system move along quite well, but we don't get it for energy. The energy that we obtain would be through consuming starch mostly. Starch is the storage form of energy in plants. Okay? You might know plant makes their own food, right? In photosynthesis. They often make more food than they need and they store the excess in the roots or in the stems, right? In the case of like potato, it's part of the root. Same thing with the carrots, but they might store it in the stems in other plants as well. And when we consume these plant parts, we are ingesting the glucose, the starch, and our body will break the starch down into individual glucose, which then we can burn as fuels. So starch is, you can see it's a combination of polymers that's non-branched and branched. And the main function for starch is the storage form of energy in plants. Do we have starch in the body? We don't, but we eat them. Okay, we eat them and then we burn them, but we don't make them. Okay, plants make them to store food for themselves. So when it's the winter, they could use it. Okay, but of course we harvest it and we eat it. What about us? What if we eat too much? Where do we store it? We store excess glucose in the body in the form of glycogen. Glycogen. It's another kind of polymers. Okay. So glycogens can be stored in muscle or it can be stored in the liver. Okay. Your liver is right here. Liver is over here. Okay. Just under your diaphragm. Okay. On the right side. And it looks like this. And it stores glycogen. If you haven't had lunch yet, and your body is, in need of energy because of the hard lesson and keeping you awake, your body will be taking the glucose from the glycogen in the liver. Right? It will, it will break off little bits and pieces of glucose here and keep you going until you eat. Okay? If you're fasting, right, then you will use your glycogen reserve, right? Slowly burn it away. So three kinds of polysaccharides: cellulose to form the fibers in plants, starch for the plants to store their sugar, glycogen for us, for animals, for humans to store our glucose. And we're going to just do one more and then we're done. Right? So this is just a picture that shows you, in the muscle, you will have the glycogen. In the potato, you will have the starch. And the leaf part that we don't eat, that's where the cellulose are. These are actual pictures of what they look like under high power microscope. Okay, there is one last polymers for carbohydrates. It's called chitin. Okay, so chitin, they are a special kind of glucose that contains nitrogen, and it makes it very, very strong. So it's excellent to form shells of animals that has like a exoskeleton. So crustaceans like crabs, lobster, shrimp, their shell contains this chitin. Bugs that have like crunchy shells, they also have chitin in their exoskeleton. We have figured out a way to use the chitins to make surgical threads. Okay? If you have removed your wisdom teeth or whatever, they stitch you up with chitins nowadays. And because it's an organic molecule, the chitin is biodegradable. It will melt in your mouth, right? And it allows your wound to heal faster and heals better. In the past, if they stitch you up after surgery, you have to go back to remove the stitches. Okay, but not anymore. Right, the surgical threads are all going to degrade on their own because they are made up of chitin. Okay, just to reiterate, we do not have chitins in our body. We don't make them. Okay, it's just something that shell animals have and bugs they have it. Right? We don't have them, and that's it. Okay, we have two more questions here. Let's just quickly do the polls, and then I will let you go. All right. If you look at the slides earlier, you will see sucrose, which is kitchen sugar, is made up of glucose and fructose. So the correct answer is D. Okay, this one is very long. We will do it together. Select all the false statements below. You might remember I told you the actual quiz, there will be some questions where there are multiple correct answers and they're worth 2 marks each. So it will look something like this. Okay? So we're looking for the false statements, the ones that are wrong. Let's see. Polysaccharides are important both for energy storage and to provide structure to cells. That's correct. Okay. Energy storage, we have starch in plants and glycogen in humans. Structure, we have cellulose in plants and chitin in crabs. So that's the correct statement. We're looking for the false one. Next one, glycogen is important both for energy storage and to provide structure for cells. That is incorrect. Okay, glycogen is only for energy storage. It does not provide structure. That's cellulose and chitin. Cellulose is only found in animals. That is also incorrect because cellulose are found in plants. Glucose, fructose, and galactose are examples of monosaccharides. If you look at the list earlier, you will see that this is correct. So we are looking for the false one. We're not going to choose this. Starch is a storage polysaccharide made by plant cells. That is also correct, and we're not going to choose it. Okay. Well, that's it for today's lesson. But before you go, I just want to remind you to go and do the self quiz, okay? I see only 2 of you have done it, and I know who you are, okay? So good job if you've done it. But for the rest of the class, if you have not done it, you need to start working on these things, okay? These are good questions to help you prepare for the quiz. Our first quiz is going to be, uh, let me just switch to student view. I think it's going to be next week, but let me just double check over here. Okay, if you go to the quiz folder, you will see it is there are the concept track questions answers, the ones that we just did in class. If you missed the answer, they are all here, and it's going to be available on 27th. Okay, so 27th is going to be, yeah, we have some time. It's going to be next week. Okay, but you should start studying. Okay, there are 25 multiple choice questions, 2 short answers, and if you go to Lecture 1, study resources, there are the answers for the study guide, and then there are the self-quiz. Okay? Please do them. And that's it for this week. Okay? Take care, guys. Get some rest, and I'll see you again next week. Bye-bye.
You, see you.
No problem.
Yeah. Bye.
Yeah, well.
Bye bye. Thank you.
Bye.